Hello everyone, welcome to this lesson. So up to this point we have learned Euler's method, we have learned Hans's method, midpoint method, and Ralston's method to solve ordinary differential equations. Now all four of these methods actually fall under a general umbrella called the Runge-Kutta methods, where the Euler's method is actually a first order Runge-Kutta because it describes the derivative of each interval using one derivative, which is the derivative at the start of the interval, and also Hans, midpoint, and Ralston methods are actually a second order Runge-Kutta because they describe each one of the intervals using two derivatives. And from this pattern, from this logic, you can deduce that a third order Runge-Kutta would use three derivatives and the fourth order Runge-Kutta would use four derivatives. Now I'm going to, in this lesson, to describe the four methods that we have covered up to this point from the perspective of a Runge-Kutta method, and also I'm going to be introducing the third order and the fourth order. And in the next lesson, we're going to be developing codes for the third order and the fourth order, and then we're going to run through examples to see how these six methods describe and solve ordinary differential equations. So actually, let's begin. So if you look at the top left here, we have the first order Runge-Kutta, and generally, from a perspective of the Runge-Kutta, it's actually described as yi plus 1 is equal to yi plus k1h, where k1 is the derivative at xi yi, which is basically the derivative at the start of the interval. So here, this is where we got Euler's method. Now, in terms of the second order Runge-Kutta, it generally defined as yi plus 1 is equal to yi plus a1 k1 a2 k2 multiplied by h. Now, how you define a1 and how you define a2 will depend on which one of these methods you're going to get. For instance, Hans's method defines a1 and a2 as 1/2. And if you look here with the midpoint method, the a1 is 0, the a2 is 1, which reduces down to k2 here, and also the Ralston, a1 is 1/3, a2 is 2/3. So this is the general description of a second order Runge-Kutta, and how you define a1 and a2 will depend on what method you are using. And if we look a little bit closer, with the Hans, we said that k1 is the derivative at the start of the interval, right? So here we have f of xi, yi, and we also said that k2 is the derivative at the end of the interval, where the y to get this k2 is actually calculating using Euler's method. And you can see here f of xi plus h, so this is the x value at the end of the interval, and this is also the y using the Euler's method, yi plus k1h. So you can see how we define k1 and k2 here. And with the midpoint, again, k1 here is defined as the derivative at the start of the interval, and here k2, which is the derivative at the midpoint, so it's xi plus k, or h divided by 2, and here we use Euler again to get this y, so it's going to be yi plus k1h divided by 2. And finally, with the Ralston, again, k1 is the derivative at the start of the interval, and this is the x value at the 3/4, and also this is using Euler to get the y value at the 3/4. Now here, so this is the second order Runge-Kutta, first order. Now let's actually look at the third order. So we know that the second order described using two derivatives. So we know that with the third order, we're going to have k1, k2, and k3. Now k1 is still defined as the derivative at the start of the interval. k2 is defined as the derivative at the midpoint of the interval. Now k3 here is what is slightly different. It is another approximation of the derivative at the midpoint of the interval, where you can see here we are using the x value at the midpoint, xi plus h divided by 2, and here we're getting a unique approximation of the y at the midpoint, which is yi plus negative k1 plus 2 multiplied by k2 all multiplied by h. In other words, we're given k1 a weight of -1, and we're giving k2 a weight of 2 and based on this equation here, we can get the y, and we can get the derivative at a new derivative at the midpoint, which we're going to call k3. So in the third order, we have the derivative at the start of the interval, the first derivative at the midpoint of the interval using k1, and then we're getting another derivative at the midpoint using k1 and k2, right? So let's actually move on to the fourth order Runge Kutta. Again, the third using k1, k2, and k3, so you can predict what the fourth is going to be k1, k2, k3, and k4. Now, k1 is the derivative again at the start of the interval. K2 is the derivative at the midpoint of the interval, where we're using k1 to get the y here. And k3 is another approximation of the derivative at the midpoint, but in this case now we're using k2 instead of k1. And k4 is now the derivative at the endpoint of the interval, and you can see here using xi plus h, and here we're using k3 to get the derivative at the endpoint. So derivative at the starting point, derivative at the endpoint, and two derivatives at the midpoint. Okay, so what have we learned in this lesson? We have introduced that the four techniques that we have learned thus far fall under the umbrella of methods called the Runge Kutta methods, where the Euler's method is actually a first order, the Hans, midpoint, and Ralston were actually second order, and we have introduced the third order, where basically the K3 is a derivative approximation of the midpoint, a very unique derivative approximation of the midpoint. Also, I forgot to mention the general equation here for the third, which is yi plus 1 is equal to yi plus 1/6. And here you have k1 plus 4 times k2 plus k3 multiplied by h. So here's how we combine the derivatives with a weight of 1/6 for all of them and a weight of 4 for k2. Here, as you can see, normally we give a weight of 1/6 to the start and end of the interval and a weight of 1/3 to the middle ones. And if we take this as a common factor, 1/6, we have a 2 next to the k2 and a 2 next to the k3. Now, in the next lesson, we're going to develop a code for a third order Runge Kutta and a fourth. And as you can predict, they're going to be just an extension of what we done with the Hans, midpoint, and Ralston. And then we're going to go through a few examples of how the first, second, and third, and fourth order would actually describe or solve ordinary differential equations. So that's it for this lesson, and I will see you in the next lesson.